Good afternoon, everyone. Hope you had a good lunch and you are not sleepy. So I'm going to try not to present you with 60 slides, probably only 12 I have. So this presentation will focus on a kind of a process, which is an end-to-end process. I work for a private company, CubeSat satellite company called Spire Global, and we actually make satellites for observing GNSS signals. But we do the whole process from the beginning to the end, and at the end of the process is data assimilation and forecast verification. So that's why we have so many co-authors on this presentation, because this is the very first time that we did this end process, and the very first time that we are seeing the impact of radio occultation data created by our own satellites on the data assimilation and the forecast. So I will just single out one co-author who is also data assimilation person, Razvan Stefanescu from data assimilation team, but the rest of the co-authors are not. They're across different departments in Spire, and that's what it actually needs to happen, collaboration across many different areas to get observations and to assimilate them. So as I mentioned, Spire, first, my outline of the talk. I will explain about the satellites that we make. Then I will go into data assimilation experiments and present some preliminary results and summarize the work. And then explaining a little bit about our satellites. We have a constellation of cube satellites. These are 3-unit satellites, and there is about, right now, about 60, more than 60 of them, and there is this one called Zupanski. Each person in our company gets to name his or her own satellite. Or I could have said maybe I am a special person, but actually that's not true. Each one will get his own satellite. But mine is here, and I'm really happy. There is also one called Alexander, which is Alexander McDonald, who leads our forecasting and data assimilation team at Spire. And as I mentioned, those satellites are really small. They're 3 U satellites, 3 units. And the size of a satellite is like, oftentimes we say, is a bottle of wine, like double this size, hopefully a good bottle of wine. And what I care about is here, RO antenna. It helps us receive RO signals, but there are many other things that engineers understand how they do and what they do. But one cool thing about those satellites is that they are in our company, and I am doing data assimilation with some other team members as well. And they actually ask us what kind of observations you would like to have and how many. And of course, I get to choose, and I can say, yes, I would like more and more radio occultation observations. But also, recently, we started adding new sensors, new receivers. So now we can even observe reflectometry signals from the GPS satellites, which actually give you information about soil moisture over land and about surface winds over ocean. Also, we are receiving signals from the airplanes, which are called ADS-B signals. So we get to choose or influence our engineering team because everything is in the company. And I feel I have power saying I would like more of those or these data, at least in theory. But sometimes it's hard to get more data. But in order to get more data, I first need to prove that the data has some positive impact. And that's what I'm trying to do now. So now I'm going to explain the data assimilation experiment, first starting from a system design, a data assimilation system that we use. And it's a very standard data assimilation system, similar to NOAA. That's NOAA one used in operations, hybrid ensemble-variational data assimilation method, ensemble Kalman filter for the ANVAR system. Unlike in NOAA, in this particular experiment, we don't use as many ensemble members. We only use 20 ensemble members. We use a specific model, which is a global atmospheric model called ANPAS, ANCAR model. It works on icosahedral grid. I think Japanese model also works on icosahedral grid. There are some similarities in those. And this is a specific resolution that we run. And we do use our own observation operator for radio occultation observations. It's a one-dimensional operator. And in this particular experiment, we don't run data assimilation on a native icosahedral model grid. It's run on a latitude, longitude Gaussian grid. So it's an approximation here. And of course, in the experiments, it's always used, all experiments are run on the same grid. It's just an extra approximation that you would not like to have. And we will move away from that approximation in the future. So experimental setup. There is a control experiment, and I put color orange on it because later on when you see the lines of root mean square errors, those will be in orange for the control experiment. And there is also the experiment with RO data. It's in blue, and you will see line in blue. So what's the control experiment? It includes all NOAA observations, typically assimilated at NOAA and SAP. Those are conventional plus satellite, plus other GPS observations, not Spire GPS, but others such as Cosmic, METOP, A, B, and so on. I have to point out that some data we don't have available. Whatever is publicly available we use, but Mesonet and some aircraft data we don't have available because those are restricted data, so those are not present. But the goal is to run an experiment that's kind of realistically presenting what a typical, say, weather forecasting center has as data. And when we add up our own Spire data to see what's the impact. An experiment that's not realistic would be just assimilating a very small amount of other data and then add up our own data, and probably you will see more impact in that case. So what's our experiment? It's a control plus Spire radio occultation observations. And we assimilate bending angle observations. That's a last process observations than some retrieval of temperature and humidity, and that's better, you know. We are a data assimilation meeting. We like raw data as much as possible. And how many profiles do we assimilate? Profile means that we have observations throughout the whole column of the atmosphere. That's one profile, and one profile can have a couple of hundreds of data points in the vertical. So typically we have only about 200 Spire profiles of bending angles over a 6-hour period, which is our data assimilation interval. So that's not that much. That's much less than, say, cosmic data. Why it's not that much? Because we are still building the system. We are still building the satellites, and we hope to have more in the future. It's the very first time that we said, let's see if we can have any impact even with 200 profiles of assimilation per data assimilation cycle. So it's not a very significant amount, but hopefully some amount that can make some kind of a bump in the forecast. That's what we were hoping when we started this. And again, there is another approximation in this experiment. Approximation here is that we didn't really evaluate our observation errors, and today and yesterday we heard about presentations about how we should estimate observation errors, taking care of the biases, though those observations are not biased, but maybe they are cross-correlated. We maybe need to do eigenvalue decomposition and cut the lowest values, or just eliminate them, as Craig said, by use them. We didn't do any of those because it takes time. So what we did, we just used the observation errors that are defined in the NOAA data assimilation system. You remember the name GFS system, or full for the NVAR, they use the same errors. But those are defined for cosmic one data, not for our data. They didn't say those are for Spire data. But those are similar enough so that even though this is an approximation, kind of the first order of accuracy, or sometimes I say in the ballpark, we are okay. So we continued with this experiment, even we do have this approximation. And now I just wanted to mention about the data assimilation period. We ran an experiment over 11 days last year in October. And I already mentioned that the data assimilation cycle was 6 hours. And then we evaluated the impact of our radio occultation data on the forecast, short-term forecast, which is in this case up to 48 hours forecast. So then, before showing you the forecast verifications, we just make a kind of just a visual checking of what's happening with data assimilation when you do data assimilation, and then check what are the changes to the analysis and to the forecast. Then you plot some fields, and what we plotted here is difference field for higher levels of atmosphere, and it was for 100 hectopascal geopotential height. And in the left-hand side, it's a difference in the analysis between the two experiments, the control and the experiment with the Spire radio occultation data. And there are some differences, a few meters in the geopotential height at that level. And then we looked what happened in the forecast, and typically you would like to see that those differences propagate in forecast, and also it's very, very reasonable to expect that those differences grow. So it looks reasonable. Then what we did, we started evaluating the forecast errors. Again, we are looking only in the higher atmospheric levels. Here we are looking from levels from left to right, 500 hectopascal level, and up to 100 hectopascal levels. Typically, the studies performed so far, European Center studies, NOAA study, UK studies, and so on, they show that the most significant impact of radio occultation observations are at higher atmospheric level. Not that there is no impact below, but the most significant impact is at those levels, and that's why we are looking at those levels first. And these are kind of errors for every data assimilation cycles. If you remember, we had 11 days of data assimilation. So we initialized those forecasts, and those are 24-hour forecasts, and cycle after cycle. Blue is typically slightly better than orange, so it means that there is a positive impact of assimilation of Spire radio occultation observations on reducing the root mean square forecast error. That's 24-hour forecast, and I forgot to say, on the upper level is temperature, and the lower three panels are geopotential height. Then looking at 48 hours, we also saw a positive impact, though probably a little bit smaller, which is again expected. We didn't have any significant impact at lower levels or other atmospheric variables such as wind, cloud variables, and those, so I'm not showing those. And then I would like to summarize what we found so far. From the 11-day experiment, we found that our Spire radio occultation observations had positive impact on the short-term forecast for temperature and geopotential up to 48 hours. That's in upper levels, which is in agreement with other studies. And we did find neutral impact below and for other variables. I'm sorry. So there I am. I think I'm going in the wrong direction. Now, future work. So I didn't mention much, but it's well known from the studies, such as one from Kukurul et al., that radio occultation, bending angle, and also refractivity observations are almost bias-free. So we will examine how this bias-free data can be used in the future to further improve the forecast. We didn't have time for that now. But what I'm really excited about, I got a promise from the satellite planning team that we will get pretty soon 4,000 to 5,000 radio occultation per day, observations per day. In the experiments that I've showed, we only assimilated 800 profiles. And just wanted to mention, this evaluation study was performed in Spire within the company. But we do collaborate with external partners to have like a third-party evaluation of our data. We have collaborations with NASA, NOAA, ESA, UK Met Office, and so on. I'm also interested, not I, but the Spire is also interested in collaboration with research scientists like data assimilation scientists like you here to evaluate our data. We can collaborate, and you can even get data for free, and especially if you have a NASA proposal. We already have a contract with NASA to give data for free for experimenting with that. So we would like to get our data more evaluated and get the best out of it. So that's it. Thank you. And of course, if you want, you can check this webpage or just send me an email or talk to me if you need more information on how to get free data.
Thank you, Dusanka.